And now in this lecture I will answer on two questions. In the first question we'll find out the area of this circle, and in the second question we'll find out the length of this line segment QB that is equals to x. So in the drawing we'll start with the first question. In the drawing we have a circle that is inscribed by this trapezoid ABCD. A trapezoid is a quadrilateral with one pair of parallel sides. This trapezoid ABCD, side AD is parallel to side BC. So in addition we know that AM equals to A units in its length, MB, line segment MB equals to B units in its length. Again, our mission is to find out the area of this circle. So first of all, when we find the center of this circle, this point is point O. And we define the point of tendency of tangent AD with this circle. This point is point P, and when we find the point of tendency of tangent BC with this circle, this point is point Q. And we will focus on this convex line point A. On this convex line point A, we have two tangents to this circle, tangent AM and tangent AP. According to rule 2, they are equal to each other. That is to say, AM equals to AP. So, I'll read the rule 2 quickly. According to rule 2, the lengths of two tangents from a convex line point to a circle are equal. So in the drawing we have a circle, and this is the convex line point B. From this convex line point B, we have two tangents to this circle, tangent PA and tangent PB, and according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So can we write rule 2 in our drawing? What was in our drawing? We have this convex line point A. For this convex line point A, we have two tangents to this circle, tangent AM and tangent AP. And according to rule 2, they are equal to each other. That is to say, AM equals to AP. But AM equals to A, therefore AP must be also equal to A units in its length. Likewise, for this convex line point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to B according to what is given as the question, therefore BQ must be also equal to B. So this is tangent BQ is equal to B units in its length according to rule 2. In the next step, we define the center, the radius of this circle as x, and we will join point O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle that is equal to x according to our definition. And because of the fact that the radius of OQ that is equal to x, the radius of Q is known to point Q, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is 1 to the point of tendency, then tangent BC will be perpendicular to the radius QO according to rule 1. If BC is perpendicular to QO, it means that this segment equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by a straight line. OP is also the radius of this circle that is equal to x. According to rule 1, because of the fact that the radius OP is equal to x, the radius OP is drawn to point P, that is the point of tendency of tangent AD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we'll do a construction. That is to say, from this point A, we will draw perpendicular on BC. Again, from point A, we will draw perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point N. By doing this construction, we can adhere those two angles. Those two angles are defined as one-sided interior angles and are located between the parallel lines AD and BC. AD is parallel to BC because ABCD is a trapezoid. Here we can implement rule 17. According to rule 17, the sum of one-sided interior angles between two parallel lines is equal to 180 degrees. So in the drawing we have line A that is parallel to line B. The red line C intersects with those two parallel lines A and B, those 2 points. Those are angles alpha and beta that are defined as one-sided interior angles. And because of the fact that those two one-sided interior angles alpha and beta are located between the parallel lines A and B, the sum of those two one-sided interior angles must be equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So we can actually implement rule 17 in our drawing. In our drawing, we have those two one-sided interior angles that are located between the parallel lines AD and BC. Therefore, according to rule 17, the sum of those two one-sided interior angles is equal to 180 degrees. But this angle equals to 90 degrees according to our construction. So 90 degrees plus the size of this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction, that is to say, from this point O, we will draw perpendicular on AN. Again, from point O, we will draw perpendicular on AN. So here, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and AN. This point is point T. By doing this construction, we will do quadrilateral AP or T. Beside this quadrilateral AP or T, we have one, two, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its size. Likewise, we'll focus on the this lower quadrilateral TOQN. Inside this quadrilateral we have 1, 2, 3 right angles. Again, the sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this profile again, in total they must be equal to 360 degrees. Therefore, this profile again must be equal to 90 degrees in its size. So the size of the big angle POQ is equal to 90 degrees plus 90 degrees, that is 180 degrees. So I write it down. The big angle POQ is equal to 180 degrees in its size. And you know that any angle that is equal to 180 degrees in its size is defined as a straight line. Therefore, line segment POQ is a straight line. Okay, again, this line segment POQ is a straight line. If POQ is a straight line, then PQ is also a straight line. Line segment PQ is also a straight line. So, shape APQN, this shape APQN consists of 1, 2, 3, 4 sides. So write it down. Shape APQN consists of 4 sides, and therefore shape APQN is a quadrilateral. This shape APQN is a quadrilateral. We have already found out that quadrilateral APQN consists of 4 right angles. And according to Rule 5, any quadrilateral that has 4 right angles must be this right angle in front of square. So we write to this quadrilateral APQN as right angle because it has 4 right angles. So I write it down. Quadrilateral APQN is a rectangle according to Rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle APQN, side AP must be equal to the opposite side NQ. But AP is A, therefore NQ must, the opposite side NQ must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ in total equals to X plus X, that is 2X. Therefore, the opposite side AN must be also equal to 2X units in its length. What is the length of this missing line segment BN? From the drawing it is very easy to see that BN equals to BQ minus NQ. So I write it down. BN equals to BQ minus NQ. So BN in total equals to BQ. BQ is B according to Rule 2. Minus NQ. NQ is A. So in total, Bn equals to b minus a units in its time. So in the next step, I'll copy this right triangle A and B in a new page, and we will implement the Pythagoras theorem on this right triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse AB of the right triangle A and B is equal to A plus B units in its length. NB equals to B minus A, and side AN equals to 2x units in its length. Here by PT is the progression for Pythagoras theorem. So actually, this is the right triangle A and B that I copied from the original drawing. In this right triangle A and B, AB squared, that is the square of the hypotenuse, equals to AN squared plus NB squared. So I write it down. AB squared, that is the square of the hypotenuse, is equal to AN squared plus BN squared. AB is A plus B, therefore AB squared is A plus B squared, and it is equal to AN squared. AN is 2x, therefore AN squared is 2x squared, 2x squared is 4x squared, plus Bn squared. Bn is B minus A, therefore Bn squared is B minus A squared. So in total we found out that A plus B squared equals to 4x squared plus B minus A squared. We will open the brackets on both sides of this equation, and we get that A plus B squared equals to A squared plus B squared plus 2 times A times B, and it is equal to 4x squared plus B minus A squared. B minus A squared equals to B squared plus A squared minus 2 times B times A. So here we have A squared on both sides of the equation, so A squared will get cancelled. And we also have B squared on both sides of the equation, so B squared also will get cancelled. After we cancel those two expressions, on this side of the equation we left only with 2AB. On the other side of this equation we have left only with 4x squared minus 2BA. So if we found out that BA equals to 4x squared minus 2BA. Here we add 2AB to this equation, and we get that two AB plus 2AB is 4AB, so 4AB equals to 4x squared. Here we divide this equation by 4, and we get that 4ab over 4 is ab, and it is equal to 4x squared over 4 is x squared. So in total we found out that x squared equals to ab. Our mission is to find out the area of this circle. So okay, we know that the area of any circle is equal to pi times the radius of the circle squared. Repeat again, the area of any circle equals to pi times the radius of the circle squared, and therefore the area of this circle must be equal to pi times the radius of this circle squared. So it is pi times the radius of this circle. The radius of this circle is x, the radius squared is x squared. So in total we found out that the radius of this circle is equal to pi x squared. So it is pi times x squared. We just right now found out that x squared equals to ab. Therefore we substitute x squared here by ab. So in total we found out the area of this circle is equal to pi times AB square units. Then again, we found out that the area of this circle, that is the area that we are looking for in this question, is equal to pi times AB square units. We finished with the first question. In the next step I will present to you the second question, and we'll solve the second question of this lecture. Our mission in this second question is to find out the length of this line segment QB that is equals to x. So we have to find out the value of x. In the drawing we have a semicircle. Line segment AB is equal to 30 units in its length. AB is the diameter of this semicircle, so we know the diameter of this semicircle is equal to 30 units in its length. In addition, we know that this is called P8, that is equal to 10 units in its length. This is called QP, that is also equal to 10 units in its length. Again, our mission is to find out the length of this line segment QB that is equal to x. We have to find out the value of x. So in the first step, we define the center of this semicircle. This point is point O. The diameter of this semicircle is equal to 30 units in its length. If the diameter is 30, the radius must be equal to half of it. That is to say, the radius of this semicircle must be equal to 30 over 2, that is 15. So we have found out that the radius of this semicircle is equal to 15 units in its length. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, that is equal to 15 units in its length. Likewise, OB is also the radius of this semicircle, that is equal to 15 units in its length. In the next step, we join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the semicircle itself, therefore OP is the radius of this semicircle, that is equal to 15 units in its length. In the next step, we will complete this semicircle to a circle. And we will extend the radius PO of this semicircle by a straight line until it touches this circle and this point. So actually, this is the touching point of the extended radius PO with this circle. So we define this touching point as point M. OM is of course the radius of this circle, that is equals to 15 units in its length. The next step, we join points M and B together by a straight line. This is angle MOB and this is angle AOP. Those two angles MOB and AOP, they are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define this vertex angle as theta, then this vertex angle must be also equal to theta according to the rule that I mentioned. So in the next step, we prove that this triangle APO is congruent to this triangle MOB. We prove that this is triangle APO. We prove that this triangle APO is congruent to this triangle MOB. So why those two triangles congruent to each other? First of all, side OP of this right triangle APO is equal to side OM of this right triangle OMB. They are both the radii of this circle. They are both the radii of this circle. Therefore, they are equal to each other. So I write it down. OP equals to OM. They are both the radii of the circle. Is equals to 15, and therefore they are equal to each other. Repeat again. Side OP of triangle APO is equal to side OM of triangle MOB. They are both the radii of the circle. This is equals to 15. Therefore they are equal to each other. In addition, those two angles are both equal to theta. Therefore they are equal to each other. According to the rule that vertex angles are equal to each other. So this is angle AOP in triangle APO, and it is equal to this angle, that is angle MOB in triangle MOB. They are both equal to theta, therefore they are equal to each other. Actually, as I already mentioned before, those two angles are vertex angles, and we know that vertex angles are equal to each other. And finally, side AO of this triangle APO is equal to side OB of this triangle OMB. They are both the radii of the circle, and therefore they are equal to each other. So I write it down. OA equals to OB. And again, side OA of triangle APO is equal to side OB of triangle MOB. They are both the radii of the circle, that is equals to 15. Therefore they are equal to each other. So we proved that those two triangles can point to each other according to side angle side rule. So that is on triangle APO congruent. This is the sign of congruent to triangle MOB according to side angle side rule. What is side angle side rule? So we have those two sides and the angle that included between those two sides, that is angle theta, in triangle APO, are correspondingly equal to those two sides and the angle that is included between those two sides, that is also angle theta, in triangle MOB. Therefore, those two triangles can go into each other according to sine angle side rule. We have those two sides and the angle that is included between those two sides that are correspondingly equal to those two sides and the angle that is included between those two sides in triangle MOB. Therefore, those two triangles can go into each other according to sine angle side rule. And from the fact that those two triangles can go into each other, we will derive that side AP or triangle AOP is equal to side MB or triangle MOB. So, as you know, AP equals to MB. So side AP equals to side MB according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AP and MB, must be also equal to each other. But it is given as the question that AP equals to 10 units in itself, so I can write here that AP equals to 10, and from this equation 10 equals to AP equals to MB, we will derive that MB is also equal to 10 units in its length. MB is also equal to 10 units in its length. This is chord PM, and this chord PM passes through point O, that is the center of this circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. So PM is the diameter of this circle. So in the next step, I'll copy this semicircle with the diameter PM and we will analyze this semicircle. So actually, this is the semicircle with the diameter of PM that I copied from this drawing, original drawing. Chord PQ is equal to chord MB, they are both equal to 10 units in their length, therefore they are equal to each other. Point O is the center of this semicircle. So in the next step, we will extend line segment PQ and line segment MB, those two line segments, until they intersect with each other. This is their touching point or their intersection point. We define this point as point E. So we extended line segment PQ and line segment MB that are equal to each other in their lengths, and in this way we created two new line segments, line segment PE and line segment ME. And we have the rule that when you extend two line segments that are equal to each other in their lengths, then the new line segment that will be created will be also equal to each other in their lengths. And therefore, the new line segment PE must be equal to the new line segment ME. Okay, when you extend two line segments that are equal to each other in their lengths, then the new extended line segments must be also equal to each other. The extended line segment PE must be equal to the extended line segment ME, according to the rules that I mentioned. So, by doing these constructions, we get the triangle PEM. Triangle PEM is an isosceles triangle because of the fact that side PE equals to side EM. Those are the two angles of the isosceles triangle PEM. They are defined as base angles, and they must be equal to each other. So anyway, I will prove that those two angles are equal to each other, according to the rule that in front of equal sides in the triangle there are equal angles. EP is equal to EM. So in front of this side EP, we have this angle PME. In front of this side EM, we have this angle that is actually angle MPE. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta, because they must be equal to each other according to the rule that I mentioned. Okay. In the next step, we will complete this semicircle to a circle. So in the drawing, we have quadrilateral PQBM. This is quadrilateral PQBM that is inscribed by this circle. And according to rule 16, any quadrilateral that is inscribed by a circle, the sum of its two opposite angles must be equal to 180 degrees. So I repeat again rule 16. According to rule 16, if a quadrilateral is inscribed by a circle, then the sum of its two opposite angles is equal to 180 degrees. So in the drawing we have, this is quadrilateral ABCD, and it is inscribed by this circle. And according to this rule 16, the sum of its two opposite angles is equal to 180 degrees. Those are the two opposite angles of quadrilateral ABCD, and therefore the sum of those two opposite angles must be equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. Likewise, those two angles are also defined as the opposite angles of triangle of quadrilateral ABCD, and therefore the sum of those two angles must be equal to 180 degrees. That is to say, angle 1 plus angle 2 is equal to 180 degrees according to this rule, rule 16. So we can actually implement rule 16 in our drawing. Why? Because in our drawing, quadrilateral QBMP is inscribed by this circle, and according to rule 16, the sum of its two opposite angles must be equal to 180 degrees. That is to say, those are the two opposite angles of quadrilateral QBMP, and therefore the sum of those two angles must be equal to 180 degrees according to rule 16. This is angle beta plus the size of this missing angle. In total, they must be equal to, in total, the sum of those two angles must be equal to 180 degrees according to rule 16. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the opposite angles of those two opposite angles in quadrilateral PMQB. Likewise, those also the two opposite angles of this quadrilateral QBMP, and therefore the sum of those two opposite angles must be equal to 180 degrees. This is angle beta plus this missing angle, in total must be equal to 180 degrees. Therefore, this missing angle must be also equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of those two opposite angles in quadrilateral QBMP that is described by this circle according to rule 16. So in total, we found out that this is angle beta, this is angle 180 degrees minus beta. 180 degrees minus beta plus beta is 180 degrees. So the sum of those two angles is equal to 180 degrees. But those two angles are defined as one-sided interangles. So we should find out that the sum of two one-sided interangles is equal to 180 degrees, and therefore those two one-sided interangles must be between parallel lines. That is to say, QB is parallel to PM, according to rule 18. So I'll repeat quickly on rule 18. According to rule 18, if the sum of two one-sided interangles is equal to 180 degrees, then they are located between two parallel lines. So in the drawing we have, this is line A, this is line B, and the red line C intersects with those two lines at A and B at those 2 points. Those are angles alpha and beta that are defined as one-sided interangles. And according to this rule 18, if the sum of those two one-sided interangles is equal to 180 degrees, then they must be located between parallel lines. That is to say, line A is parallel to line B. So whenever you have two one-sided interangles that the sum of them is 180 degrees, then they must be between parallel lines. They already implemented rule 18 in our drawing, because in our drawing we have only found out that the sum of those two one-sided interangles is 180 degrees, and therefore, according to rule 18, there must be between parallel lines. That is to say, QB is parallel to PM. So I write it down. QB is parallel to PM according to rule 18. In the next step, I copy this semicircle with the diameter PM, and we will continue to analyze this semicircle. So actually, this is the semicircle with the diameter PM that I copied from the original drawing. We'll join points O and B together by straight line. Point O is the center of the semicircle, point B is the point of the semicircle itself, therefore OB is the radius of this semicircle, that is equal to 15 units. Those two angles are defined as alternating angles, and they are located between the parallel lines QB and PM. QB is parallel to PM according to Rule 18. Rule 18, yes. QB is parallel to PM according to Rule 18, and those two angles are defined as alternating angles, and they are located between the parallel lines QB and PM. And therefore, according to Rule 15, they must be equal to each other. So I repeat quickly Rule 18 or Rule 15. According to Rule 15, alternating angles between parallel lines are equal to each other. So we have in the drawing line A that is parallel to line B. The red line C cuts those two parallel lines A and B at those 2 points. It intersects with the two parallel lines A and B at those 2 points. Those two angles alpha and beta are defined as alternating angles, and are located between the parallel lines A and B, and therefore they must be equal to each other. That is to say, alpha equals to beta. So whenever you have alternating angles that are located between parallel lines, then they must be equal to each other in their sizes. As already mentioned before, those are two alternating angles that are located between the parallel lines QB and PM, and therefore they must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to Rule 15. Okay, so in the next step, I will present to you the law. In the next step, I will present to you the law of cosines, and we will implement the law of cosines on this green triangle POQ, and on this white triangle QOB. So what is the law of cosines? The law of cosines is true in any triangle. So this is triangle ABC, that could be any triangle. The length of side AB is A units, side AC equals to B units in its length. This is side BC, that is equals to C units in its length. This is angle theta. This triangle ABC, that could be any triangle. The following equation is true, that cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, in this triangle ABC, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So, in the next step, we will implement the law of cosines in this green triangle POQ. So, I'll copy the green triangle POQ in the new page, and we will implement the law of cosines in this green triangle. This is angle alpha, and again triangle. So finally, this is the grand triangle POQ that is going from this volume. So in the next step, we'll implement the law of cosines on this triangle POQ. So according to the law of cosines in this triangle POQ, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. I repeat again, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. So I'll write it down. This will be equation 1. Cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. In the next step, I'll copy the right triangle OQB, this right triangle OQB in this page, and we'll implement the law of cosines on this right triangle, triangle OQB. This is side QB. That is the line segment that we are looking for in this question. It is equal to x. And our mission is to find out the value of x. So QB equals to x. This is the line segment that we are looking for in this question. This is again alpha. So copy this right triangle QOB here. So according to the law of cosines, in this triangle QOB, this will be equation 2, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. Repeat again, this right triangle QOB, according to the law of cosines, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So we have two different equations for cosine alpha. Therefore, we create equation 3 that says that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Repeat again. Actually, equation 3 says that cosine alpha according to equation 1 equals to cosine alpha according to equation 2. So cosine alpha according to equation 1 is 15 square plus 15 square minus 10 square divided by 2 times 15 times 15. And it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 is equal to x square plus 15 square minus 15 square over 2 times x times 15. Okay, so if we found out that cosine alpha according to equation 1 equals to cosine alpha according to equation 2. So, in the denominator of those two expressions, we have 2 times 15. So 2 times 15 will get cancelled. After we cancel 2 times 15, in this side of the equation we have 15 square minus 15 square is of course 0. So here we left only with x square over x. X square over x is x. So in total, in this side of the equation we left only with x, while on the other side of this equation 3 we left with 15 square plus 15 square minus 10 square divided by 15. So in total, according to the equation 3, what we found out that x equals to 15 square plus 15 square minus 10 square over 15. So x equals to 15 square is 225. So 225 plus 225 is 450 minus 10 square. 10 square is 100, so it is minus 100 over 15. So x equals to 450 minus 100 is 350 divided by 15. Here we divide both the numerator and the denominator of this number by 5, and we get that 350 over 5 is 70 and 15 over 5 is 3. X is QB. So found out that the length of line segment QB is equal to x. It is equal to either 70 over 3 units in its length, or in terms of numbers it is 23 and 30 units in its length. Repeat again. Actually found out that the length of this line segment QB that is equals to x is equal to either 70 over 3 units in its length, or in terms of numbers, the length of this line segment QB that is equals to x is equal to 23 and 3 units in its length. So we finish with the second question. In the next step, I will summarize the lecture. I will start with the first question, of course. So our mission in this first question is to find out the area of this circle that is inscribed by trapezoid ABCD. The definition of a trapezoid is a quadrilateral with one pair of parallel sides. Again, a trapezoid is a quadrilateral with one pair of parallel sides. This trapezoid ABCD, side AD is parallel to side BC. Again, our mission is to find out the area of this circle that is described by this trapezoid ABCD. In addition, you know that this is line segment AM, this is equals to A units in its length. This is 97 MB, that is equals to B units in its length. And our mission is to find out the area of this circle. So first of all, we define the center of this circle. This point is point O. We define the point of tendency of tangent AD with this circle. This point is point P. And finally, we define the point of tendency of tangent BC with this circle. This point is point Q. So here we can implement rule 2. If we focus on this common sum point A, from this common sum point A, we have two tangents to this circle, tangent AM and tangent AP. According to rule 2, they are equal to each other. That is to say, AM equals to AP. But AM is A according to what is given as the question. Therefore, AP must be also equal to A units in its length. Likewise, if we focus on this common sum point B, from this common sum point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM is B, according to what is given as a question. Therefore, BQ must be also equal to B units in its length. In the next step, we join points O and Q together by straight line. Point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle. We define the radius of this circle as x, therefore OQ equals to x. And because of the fact that the radius OQ is equals to x, the radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by straight line. OP is of course the radius of this circle, that is equals to x. And because of the fact that the radius OP is 1 to point P, that is the point of tendency of tangent AD with this circle, whenever the radius is 1 to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did a construction, that is to say, from this point A, we do perpendicular on BC. Again, from point A, we do perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We find the touching point of the perpendicular from point A and BC. This point is point N. By doing this construction, we created here those two angles. Those two angles are defined as one-sided interangles, and they are located between the parallel lines AD and BC. Why AD is parallel to BC? Because of the fact that ABCD is a trapezoid, and this trapezoid ABCD, side AD is parallel to side BC. So those two one-sided interangles are located between the parallel lines AD and BC, and therefore the sum of those two one-sided interangles must be equal to 180 degrees according to rule 17. But this angle equals to 90 degrees according to our construction. So 90 degrees plus the size of this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did another construction, that is to say, from this point O, we do perpendicular on AN. Again, from point O, we do perpendicular on AN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O, and again this point is point T. By doing this construction, we consider the small quadrangle APOT. Inside this small quadrangle APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. Likewise, inside the lower quadrangle TOQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So the size of this big angle POQ, in total is equal to 90 degrees plus 90 degrees, that is 180 degrees. So angle, the big angle POQ is equal to 180 degrees in its size, and we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, line segment POQ is a straight line. Line segment POQ is a straight line. If POQ is a straight line, then PQ is also a straight line. PQ is a straight line, and therefore, shape APQN, this shape APQN consists of four sides. 1, 2, 3, 4. And because of the fact that APQN consists of four sides, it is a quadrilateral. So shape APQN is a quadrilateral. They already found out that in quadrilateral APQN we have four right angles. And according to rule 5, any quadrilateral that has four right angles must be a rectangle, if not a square. So we refer to this quadrilateral APQN as a rectangle because it has four right angles. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle APQN, side AP must be equal to the opposite side NQ. But AP is A, therefore the opposite side NQ must be also equal to a unit in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ in total equals to x plus x, that is 2x, therefore the opposite side AN must be also equal to 2x units in its length. What is the ref of this missing 97 BN? From the domain it is very easy to see that BN equals to BQ minus NQ. Again, BN equals to BQ minus NQ. So BN equals to BQ, that is B, minus NQ, that is A. So in total BN equals to B minus A units in its length. AB equals to A plus B units in its length. So in the next step I copied the right angle A and B. In the new page we implemented the Pythagoras theorem on this right angle A and B. According to the Pythagoras theorem, in any right angle the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually this is the right angle A and B. This is a point from the original domain. In this right angle A and B, according to the Pythagoras theorem, AB square, that is the square of the hypotenuse, is equal to AN square plus NB square. AB is A plus B, therefore AB square is A plus B square, and that is equal to AN square. AN is 2x, therefore AN squared is 4x squared plus BN square. BN is B minus A, therefore BN square is B minus A squared. So in total we found out that A plus B squared equals to 4x squared plus B minus A squared. We open the brackets on both sides of this equation and found out that A plus B squared equals to A squared plus B squared plus 2 times A times B, and it is equal to 4x squared plus B minus A squared. B minus A squared equals to B squared plus A squared minus 2 times B times A. So here we have A squared on both sides of the equation, so A squared will get cancelled, and we also have B squared on both sides of this equation, so B squared also will get cancelled. After we cancel those two expressions, in this side of the equation we left only with 2AB, while on the other side of the equation we left with 4x squared minus 2AB. So in total we found out that 2AB equals to 4x squared minus 2AB. Here we added 2AB to this equation, and finally found out that 2AB plus 2AB is 4AB, so 4AB equals to 4x squared. Here we divided this equation by 4 and finally found out that 4AB over 4 is AB, and 4x, it is equals to 4x squared over 4 is x squared. So in total we found out that x squared equals to AB. Our mission is to find out the area of this circle. Actually, you know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of this circle must be equal to pi times the radius of this circle squared. So it is pi times the radius of this circle. The radius of this circle is x, therefore the radius squared is x squared. So in total, the area of this circle must be equal to pi x squared. But we already found out that x squared equals to AB. So we substitute x squared here by AB. In total, we found out that the area of this circle is equal to pi AB. So the area of this circle equals to pi AB square units. We finish with the first question. In the next step, I presented you the second question and solve the second question of this lecture. Our mission in this second question is to find out the length of this line segment QB that is equal to x. We have to find out the value of x. In the original drawing, we had a semicircle, and we know that line segment AB equals to 30 units in its length. AB is the diameter of this semicircle, so we know that the diameter of this semicircle is 15. Therefore, the radius of this semicircle must be equal to half of it. That is to say, it must be equal to 30 over 2, that is 15. So the radius of this semicircle is 15. In addition, we know that this is called P8, that is equals to 10 units in its length. This is called PQ, that is also equals to 10 units in its length. And this is line segment QB, that is the line segment that we are looking for. So we have to find out the length of this line segment QB, that is equals to x. We have to find out the value of x. So first of all, we define the center of this semicircle. This point is point O. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle. That is equals to 15 units in its length. Likewise, OB is also the radius of this semicircle. That is equals to 15. OP is also the radius of this semicircle. That is equals to 15. In the next step, we completed this semicircle to a circle, and we extended the radius PO of this semicircle until it touches this circle. This is the touching point. So we defined the touching point of the extended radius PO with this circle. This point is point M. OM is of course the radius of this circle. This is equals to 15 units in its length. In the next step, we join points B and M together by a straight line. Those angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if this is angle theta, then this angle must be also equal to theta, because they are equal to each other according to the rule that I mentioned. So in the next step, we prove that this triangle APO can go into this triangle OMB. So why those two triangles can go into each other? First of all, side PO of triangle APO is equal to side OM of triangle OMB. They are both the radii of the circle, and therefore they are equal to each other. In addition, those are vertex angles, and you know the vertex angles are equal to each other. And finally, side OA of triangle APO is equal to side OB of triangle OMB. They are both the radii of the circle, and therefore they are equal to each other. So we shall prove that those two triangles can go into each other according to side angle side rule. We have those two sides, and the angle that is included between those two sides in triangle POA are correspondingly equal to those two sides, and the angle that is included between those two sides in triangle BOM. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we derive that side PA of triangle OPA is equal to side BM of triangle OBM. AP equals to MB. According to the rule that corresponding angles in corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides PA and BM must be also equal to each other. But it is given as the equation that PA equals to 10. So we can write here that PA equals to 10, and from this equation 10 equals to AP equals to MB. We will derive that MB is also equal to 10 units in its length. MB equals to 10 units in its length. PM is a chord that passes through point O, that is the center of the circle, and you know that any chord that passes through the center of the circle must be the diameter of the circle. So PM is the diameter of this circle. So in the next step, I copy this semicircle with the diameter PM, and we analyze this semicircle. So this is the semicircle with the diameter PM that I come from the Zodiac domain. PQ equals to 10 units in its length, and B also equals to 10 units in its length. We extended those two chords until they intersect with each other at this point E. And actually, whenever you extend two line segments that are equal to each other in their lengths, then the new extended line segments must be also equal to each other in their lengths. So we extended line segment PQ and line segment MB until they intersect with each other at point E. Therefore, the new line segments PE and ME must be also equal to each other according to the rule that I mentioned. So PE equals to ME. PE equals to ME. So triangle PEM is an isosceles triangle. And you know that those two angle bases of an isosceles triangle must be equal to each other. Anyway, I proved that those two angles are equal to each other. Why those two angles are equal to each other? Because we have the rule that in front of equal sides in the triangle there are equal angles. So in front of this side EP in triangle EPM, in front of this side EP we have this angle, in front of this side EM we have this angle. So, and because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta, because they must be equal to each other according to the rule that I mentioned. So in the next step, I completed this semicircle to a circle. So in the drawing we have quadrangle PQMB that is described by this circle. And according to rule 16, any quadrangle that is inscribed by a circle, then the sum of its two opposite angles must be equal to 180 degrees. So this quadrangle is inscribed, quadrangle PQMB is inscribed by this circle, and therefore the sum of those two opposite angles must be equal to 180 degrees. But this angle is beta, so angle beta plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 16. Therefore this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the opposite angles in a quadrangle that is described by a circle according to rule 16. Likewise, according to the same logic, the sum of those two opposite angles in quadrangle PQBM must be also equal to 180 degrees. But this angle is beta, therefore this missing angle must be also equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the opposite angles in quadrangle PQBM that is inscribed by this circle. Anyway, we proved, we actually found out that this is angle beta. This angle is 180 degrees minus beta. 180 degrees minus beta plus beta is 180 degrees, of course. So those two one-sided interangles, the sum of those two one-sided interangles is 180 degrees. And therefore, whenever you have two one-sided interangles that the sum of them is 180 degrees, according to rule 18, they must be between parallel lines. And therefore, QB must be parallel to PM according to rule 18. Again, QB is parallel to PM according to rule 18. Okay. In the next step, I copied this semicircle with the diameter PM, and we continue to analyze this semicircle. Okay, this is the semicircle with the diameter PM that I copied from here, from this drawing. And point O is the center of this semicircle. OP equals to OM equals to OQ equals to OB. The above the area of this semicircle that is equals to 15 units in its length. PQ equals to 10, MB equals to 10 also. And those two angles are defined as alternating angles and they are located between the parallel lines QB and PM. Again, QB is parallel to PM according to Rule 18. Repeat again, those two alternating angles are located between the parallel lines QB and PM, and therefore they must be equal to each other according to Rule 15. So those two angles are equal to each other, and so if this angle is alpha, then this angle must be also equal to alpha because they are equal to each other according to Rule 15. So in the next step I presented to you the law of cosines, and we implemented the law of cosines in this great triangle POQ and in this right triangle OQB. So what is the law of cosines? Actually the law of cosines is true in any triangle. This is triangle ABC, that could be any triangle. In this triangle ABC, side AB equals to A units in itself, side AC equals to B units in itself, and side BC equals to C units in itself. This is angle theta. In this triangle ABC, that could be any triangle, the following equation is true. That cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So in the next step, we implemented the Pythagoras theorem on this, implemented the law of cosines in this triangle PQO. So go ahead and copy this triangle PQO in a new page, and we implemented the law of cosines in this triangle. So here, this is the green triangle PQO that we call it from this drawing. According to the law of cosines, in this triangle PQO, cosine alpha equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. Again, cosine alpha equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. This is equation 1. In the next step, I copied this right triangle QBO here, and we implemented the law of cosines in this right triangle QBO. This is the right triangle QBO that I copied from this drawing. In this triangle QBO, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. I repeat again, this triangle QBO, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So we have two different equations for the value of cosine alpha. Therefore, we created equation 3 that states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. So, equation 3 states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. So cosine alpha according to equation 1 equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. And it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. Okay, so in the denominator of those two expressions, we have 2 times 15, so 2 times 15 will get cancelled. Now take cancel 2 times 15. Here we have 15 squared minus 15 squared, that is 0. So in this side of the equation, we left only with x squared over x. X squared over x is x. So here we left only with x. This side of the equation 3. While in the other side of this equation 3, we left with 15 squared plus 15 squared minus 10 squared over 15. So in total, according to equation 3, we actually found out that x equals to 15 squared plus 15 squared minus 10 squared over 15. 15 squared is 225, so 225 plus 225 is 450, minus 10 squared is 100, so it is minus 100 over 15. So in total, we can find out that x equals to 450 minus 100 over 15. 450 minus 100 is 350, so in total this expression equals to 450 over 15. So in total, we can find out that x equals to 350 over 15. Here we divided both the numerator and the denominator of this number by 5, and we found out that 350 over 5 is 70, and 15 over 5 is 3. So in total, we found out that the length of this line segment 97 cubic that is equal to x, which is equal to either 70 over 3 units in itself, or in terms of numbers, the length of this 97 cubic that is equal to x is equal to 23 and third units in its length. Okay, thank you very much.